recording now. Okay, back to regression. Okay, remember from regression a couple of main topics. It's basically it's a continuation of correlation. It utilizes the correlation coefficient, the formula that basically creates a ratio between the sum of products between the actual deviations divided by the square root of the product of the sum of squares, which is the sum of the square deviations. Thereby, it basically builds a correlation between the dependent variable on the y-axis and the independent variable on the x-axis, and has a built-in standardization process. So you have a difference between the mean and all the values in your data set divided by a Markov variability, which is the sum of squared deviations. Thereby, it follows a standardization process, and that's why you can utilize the correlation coefficient to determine, using standardized x values, to predict standardized y values, indicated as set y hat. And this knowledge is very powerful because that really allows for you to create your line of best fit, which is basically a regression function. And that regression function follows the layout or the outline and the approach of a linear equation. And that linear equation consists out of two parts. One of them is the slope, the other one is the intercept. So we've done this example. We've done this example. This basically is your regression equation. It basically has an intercept A and a slope B. So I learned it was y, and y equals k multiplied by x plus d. So k and d, you did it with m and a's. So various concepts apply, but basically the same concept is here found with intercept and slope. Intercept, as per definition, is where the x value is 0. The slope is the increase in the dependent variable with an incremental increase of 1 unit of the x-axis, bless you. So this means we can basically predict every value of the dependent variable based on our independent variable. So we have calculated. So we did the calculations, right? So set y hat, and set that y hat basically indicates it's a predicted y. It's a predicted value for the independent, for the dependent variable is calculated as our correlation coefficient multiplied by a standardized x, and that could apply for every x. And basically is then following the outline of the regression equation. Then we have the standardization procedure. We know that was chapter 6. That is x minus mx divided by the standard deviation. Same concept as we did with standardization. So basically, when you want to calculate, so you can predict every y value for a standardized x. So if you predict your y value for where x equals 0, you essentially have your intercept. This is how you can determine the intercept, which we did for our example, right? And basically you calculate 0 minus your mean, and you divide it by the standard deviation. That gets you that intercept. If you then calculate that predicted y for where your x equals 1, you have your slope. And that slope is the incremental increase with 1 unit of the x-axis. That basically gives you that increase. You just have to calculate whatever you calculated for your x equals 0, you subtract that from where x equals 1. That's your slope. That's how easy that is. You can also calculate a little bit fancier by calculating y2 minus y1. So y2 could be this one minus y1, which could be 4. So that's the next smaller one, divided by x2 minus x1. In that way, you don't even need to know those increments of 1 because you have a normalization in there for the units on the x-axis. So if you calculate y2 is that value minus y1, which is that value, divided by x2 minus x1, you get an automatically you get a normalization for the x values because you're dividing it by 5 minus 1, which is 4. So you automatically get it down to 1 increment increase. So that's the slope again. So, but make sure that you understand the definition of the slope. So we fit that line of best fit through this scatter. That's our example of the back depression inventory score. That basically allowed us to minimize the distance between the individual point and the line of best fit. The method that is being used, and I'm not sure, I don't think that's in any of the course questions. So fitting a line like that through your scatter, there are various methods that you can use to do that. But we use the method basically that is consistent with the calculation of the correlation coefficient. And the way you're calculating this is essentially by minimizing the squared deviations between the individual point and your predicted value. So you minimize the deviations. Subsequently, you minimize the squared deviations. Subsequently, you minimize the sum of squares of these, as we have learned, residuals. Residuals is the distance of the individual points to the predicted value. You minimize the distance of these residuals. So you minimize the sum of squares of the residuals, and that's how you fit your line for your entire scatter. The method is called, it's a least square approach. So you use the smallest square. There's another approach, which is maximum likelihood estimation, which is used for more advanced probabilistic models, which you don't need to know. But basically, it's just that you heard the term. It's a least square fit. So predictions have errors. So you want to, bless you, you want to predict it as accurate as possible, right? But as you can, bless you, as you can imagine, you cannot predict a real value. So if you have a back depression inventory score and you mean to predict depression for an individual just by asking the individual, okay, so how many stressful life events did you have? That's a stretch, right? It's not that easy. So obviously there's a lot of deviation from the truth, and this is error in predictions. And that's basically then quantified as the accuracy of a model. And this variability needs to be measured. And this is measured by the standard error of the estimate. So this standard error is basically the distance between the regression line and the actual data point. With this being the obvious prediction, showing a depiction of two different prediction accuracies. We have the more accurate prediction here, and the yes.
How is this different from, like, to me when I look at this, I think of like just averages in a sense, because it's kind of like an overall average of like the data, meaning like it's like a middle line. Like if you look at like a scatter, like this is a scatter chart, like the trajectory of what the data is just like the middle of the line. So how does it differ than like calling it?
Yep, and you're not far off, because essentially what you're doing with building a mean.
Right. So then, like, what's the point of it? Like it's quite visually, but I mean, it's not really like I think even without the line, anybody can see like the direction of the data. Anyone can see, oh, that's the mean of something. Like,
but it's not. So the difference is that you mean to improve the estimate of what that expected value is, right? If you say, okay, I only want to know the mean of your dependent variable, and it's a very good question that you're asking, because essentially the mean is nothing else but bad. You're right, because you mean to get the smallest squares, right? So the smallest sum of squares. That's why you fit the central tendency and you compute the sum of all the data points and you divide it by the number of the data points. Same concept applies here. Yes, you're right. But the difference here is really if I were to predict that scatter only by the mean, that would be a flat line. And that flat line is not an accurate prediction of your data because it has a direction in the space between the dependent and the independent variable. And the mean doesn't take into account this association between the dependent and the independent variable.
It's like this, you're going according to the data. Like the line goes according to the data.
The line goes according to the data from both axes. That makes it different from the mean because the mean only focuses on the dependent variable. That makes it superior to the mean. But you're asking a good question because essentially what you're doing with the proportionate reduction of error, the R squared, the coefficient of determination, you're doing nothing else. You're comparing your prediction estimate or your prediction equation to just using the mean of your dependent variable. And that's this equation, right? So if we have a sum of square total, the sum of square total is the actual y predicted as predicted in reference to the mean of y. And so this is the sum of square total. That's the sum of square that we calculate in the spreadsheet, if you remember. If you subtract from that your sum of squares error, which is your leftover error after fitting that regression equation, you only get the leftover error that your regression equation wasn't able to predict. And the corresponding visualization is this. We have here the mean of y. These are the actual deviations, which we're squaring and summing up, and we're getting our sum of squares, which is basically our denominator. And now we're calculating the proportion of which we were able to predict. And that's basically the so-called residuals. So that's the distance of the individual points to the regression line. And this is what our regression function has improved in terms of the accuracy of our prediction. And this reduction of error, that is what is being quantified in the R square.
This is like in everyday life. Like, for example, the last 2 points, like
Yep.
you can calculate what they, even though it's going in like an upward slope, like, and the bottom one is so far away, like it regresses a lot versus the top one. Like everyday life, when you look at this sort of chart, like how is it helpful, like statistically, to know, like, oh, because at the end of the day, if you look at this, you're gonna think, oh, like this company's whatever, it's going uphill, but it's not the truth if you look at like all the regressions. So it's kind of misleading.
Well, it's the regression to the mean problem, right? The way this is quantified, it will always pass through the mean. So you have here a mean and you have here a mean, and that regression function needs to go arithmetically through that mean. That's part of this standardization, that internal standardization of the correlation coefficient. What you're seeing here is something that you see quite commonly. The further you go away from the means, the more outlier you see. Because particularly when you extrapolate a regression function in RAM, where you don't have actual data points and you don't have the majority of the data, you will see outliers that kind of, they may change the direction, but they're not having the weight that it will have through that scatter, because that's where the bulk of the data is. And that's a well understood problem. That's why dealing with outliers in regression is quite complicated. That's why it tends to go towards categorization. How is that relevant? Relevant. So regression analysis you use in every walks of life, like literally every walk. It's like you open your phone, there are a million regression analyses going on. different regression, more advanced regression analysis. You've heard of machine learning and artificial intelligence for sure. This is all mainly logistic regression, which uses the same principles. Those of you that have played around with ChatGPT or regression methods in their basics, advanced obviously than in further states, but it's the same concept. And the accuracy at more extreme values. So when you come up to individuals up to like 6 stressful life events, to basically go back to apply to that use case, to that example, if you have somebody with 6 stressful life events as compared to the bulk of the data that had like 2 or 3, that's a different individual, right? It's harder to predict because it changes the nature of things if you're more in the extremes for different reason than the association you're actually looking at.
So you're looking more for the difference rather than the.
You're looking at the difference of all the data. So these are population models, right? And also for many prediction models, it's like sometimes you can't employ it on all the populations you're actually interested in. You develop that model and then you test it in different populations. When you develop prediction models, essentially what you do, you create a subset, which is your training population, your training cohort, and then you employ it in a testing or validation cohort. So it's problematic, right? And outliers are definitely confounding your thinking in that regard. That's a very good question. Yes, Friday.
Would you have us draw the line of estimate? Like you're gonna ever ask us to draw?
No, I encourage you to use Excel in case you're being asked to use any form of depiction. You will definitely on the homework. Yes, you can use the formula, but again, I would encourage you to use Excel. On the homework, you're doing scalar plots. But yeah, definitely recommend Excel. Okay, any other questions? But really memorize this. Again, if you're going anywhere further in any of the biological sciences, you will deal with R-squared, you will deal with regression. You will use all these methods, or at least you will have to interpret them. Okay, good. Okay, so mean and the residual error that is left over after employing the line of that least square approach to estimate a regression function. Regression to the mean, exactly that phenomenon that you see, that extreme scores over time tend to gravitate against back towards the mean for the very same reason as approximations with regression essentially always have to go go through the mean of your x and y variables. So definitely you have limitations. The limitations that are listed here. So you do have mostly retrospective data. Correlational analysis is most often used in retrospective data, where basically you have data that was collected over time, and then at the end of the day, somebody comes up with an idea, it's like, let's look for a signal in our data. That's when you use correlation. You also can use it for randomized data, prospectively studied data, but that's a different conversation, please. But basically, it's very often used for retrospective data. So independent variable is a scale variable. So that's kind of right now what we're dealing with. So basically, we have an independent and dependent variable that are scale variables. So that's used in correlation. In regression, you have a little bit more freeway, a little bit more wiggle room. So you can also include categorical variables. The way you would do that, again, if you include in a multivariable regression an additional term, which is a categorical variable, you're basically looking at this in a way that you built 2 different subsets of your data. Let's say this is an inherently different group than this group. And you build a regression model that is parallel shifted towards that different group. That would be done in multivariable regression. But more about that in a second. Okay, so we're visualizing and we're standardizing the residual error. This residual error is then used for the estimation of the proportionate reduction of error, the coefficient of determination, which basically quantifies the accuracy of your model. Regression to the mean we talked about, and now we're getting to multiple regression. So multiple regression is a statistical technique that includes 2 or more predictor variables in a prediction equation. And that's interesting, because when you think about it, you have an prediction based on one model, and we talked about this. It's like, how well can you really predict depression using stressful life events only? That's just not enough, right? That's not enough inputs to really have an accurate prediction. And one way to do that is by basically take a second variable into account. And the example here is to add the sleep disturbance score. So basically you're still trying to predict your depression score, but now you're not only taking into account the stressful life events, but you also take into account, does the patient actually have problems sleeping? As we all have experienced, sleep disturbance can be quite debilitating, can be quite terrible. And if you have constant problems sleeping and you have bouts of insomnia, that will basically change your perception of life. And we're going to do this as an example today. You should have the data on Canvas. Please confirm that you do. Anybody? Do you have the right data? No. Module 20, 21. Do you have the right data?
It's the same as
It's the same. Okay, that's a little bit annoying.
Like there's two, the discussion, topic number 9, but then there's also a copy.
Okay, that is my bad. Sorry for that. Yep, that is my problem. Let's quickly fix that. Okay, module 21, linear regression. Continued. Okay, my bad. Got the wrong one. So sorry for that. I should have checked that earlier. So
For further discussion 9, there's 2. So what's the second? The second one just looks like a copy. It's the same as the one above.
yeah, it's a copy from. You can disregard this one. Good. Okay. So we're going now into our file. We have this completed. Okay. So what we need to do now, we need to first quantify. So we remember from the completed file that we had we basically found the last time our prediction. If you remember, the back depression inventory score showed that it was to be predicted was 3.2 multiplied by x plus 9.5. That was the regression equation we came up last time. We quantified it using various methods, but we calculated the correlation coefficient. We quantified based on that the R squared, which can be quantified either by calculating the square of R, or alternatively, by calculating the total variability, which is the sum of squares of the dependent variable, which we calculated as 788. And then we have a y hat, which is our predicted, bless you, our predicted y, which basically was calculated as per our regression equation, which we can see here. So that's B2, our intercept, our slope multiplied by the individual x of the individual patient plus the intercept. So this is how you can calculate it. And please make sure that you know how to calculate a predicted y, because that's quite a common quiz question. And that's very simple to do, right? You just need to know how to calculate slopes with the individual x's and add an intercept. Then based on that, we basically calculated a residual error, which is our y hat, our predicted y, minus our actual value, our actual dependent variable for that individual, gets us a residual error, which is our residual. And then we squared that, and we got here the residual error. So now having the total error minus the residual error gets you the predicted error, that actually the prediction of the regression equation was able to kind of explain away. And we're basically calculating this difference and calculating that as a proportion of the total error. And that is our proportionate reduction of error. So that's the sum of square regression here. That's the difference between the total error minus our residual error. So this is what was explained by our regression. And the regression, the R2 is then basically, the R squared is basically nothing else but this as a proportion of this. Good. So now we're just going to do the same thing. So now we have on sheet 2, now we have on today's module, we have the sleep disturbance score as an additional variable. So now you're gonna wonder how we're gonna approach this, but this is now where multiple regression comes into place. So multiple regression basically takes into account 2 variables rather than 1 variable. I spare you the details on how to do that. That becomes more tricky, and that's where you do maximum likelihood estimation and becomes more tricky. But basically what you do is you're calculating here, again, predicting the depression score. You're calculating this utilizing both variables, and you incorporate them in one regression model. What you get again is coefficients. So now we're moving away from calling them slopes. Now it's a coefficient. So these coefficients are basically nothing else but slopes. You can call them a slope estimate. Your constant is just with a univariate. So you characterize univariate as the dependent variable being predicted by one independent variable. You calculate a multivariable regression as one dependent variable predicted by two or more variables. So now here we have two variables, so this is a multivariable regression. Or multiple regression, the multivariate regression. So they are synonyms that are being used for this topic. And you have now, again, you have an unstandardized coefficient. Basically, this is the intercept. This is the actual value for the intercept. So your back depression inventory score has an intercept of minus 4.117. Why is it negative? Because you would need to include this in your regression equation. And basically, everybody has sleep problems. So these coefficients are basically then building on this intercept. So none of the individuals who truly had a negative score. So that intercept is basically a mathematical construct. It's an extrapolation towards zero, allowing that prediction then in the positive form. So basically, these are the slopes. These are the respective standard errors of your estimate using this coefficient. And these standard errors then distribute again with residuals around your estimate, allowing you to quantify your T. And using this T, using the T-score table and the exact same thresholds that we discussed before, you can again quantify the p-value of your estimate. So that's the probability of this estimate actually being truly a reliable estimate. And yeah, then you have the standardized coefficients. This is basically standardized, taking the intercept out of the equation, standardizing it with the mean of the respective estimate. And this can be seen somewhat as a weight in the prediction, but it's it's less used. What you really are interested in are these unstandardized coefficients. Why is that? Because if we carry this over now, so we're copying this now in our Excel spreadsheet, because what you can do with, so we have now two equations, right? So we remember we have two equations. We have here equation number one. Equation number one was the equation that we basically calculated here. So that is this equation. So we had the univariate equation, and we have now the multivariate regression. So this is univariate regression, and here we have multiple regression. So these two allow you now to estimate your dependent variable. Your outcome variable remains the depression score. So if we are now calculating, let's use model one. Let's use y hat univariate and y hat multi. So if we were to calculate now our univariate dependent variable using the univariate regression model, we're basically calculating 3.24 multiplied by our stressful life events plus the intercept of 9.542. So that's basically the estimate for a multivariable regression. So this is how you can estimate it, right? We did that. So you calculate now the averages and the standard deviations. We can do that too. The average of this, stressful life events, then the standard deviation gives us a mark of the central tendency and of the standard deviation. And we can now calculate, bless you, we can now calculate quite simply the residuals. Residuals y hat uni. So that's basically nothing else but this minus this squared gets us now an estimate of the residuals. And the sum of this is basically that residual error that we quantified before. So first, we also need our squared deviations. That is now this y minus our mean logged in squared. And that is now our sum of squares. So that's the total variability. We calculated this last time. So we have a total variability of 788. We have a residual error of 526. And now we're trying the same exercise with multiple regression. So we know now that we have here the slopes and we have an intercept. So what are we going to do? So we do y hat multi is now nothing else but 1.194. That's slope for life events multiplied by the life events plus 2.089 multiplied by sleep problems, sleep score, minus 4.117. So that's the equation that we need to use from this multiple regression output. So utilizing this now in that fashion gives us 1.194 multiplied by our life events plus 2.089 multiplied by the sleep disturbance score minus 4.117 as the intercept. If we're propagating this formula now all the way to the end, we can now in the next step calculate now the standard the error average and the standard deviation. And we see already that the standard the average is smaller. The standard error, the standard deviation is larger. So basically what's also interesting, and pay attention to that, because the model is fitted in a way that it's getting purportedly more accurate because we have an additional variable. but you also get a prediction of here a negative dependent variable, which is unfortunately one of the prices that is sometimes paid, that when you overfit the model and this individual points are not really fitting with the overall model, you get unreasonable values. If that is getting too frequent, you kind of overfit that model. So now with y hat multi, we're going to do now the same thing as we did with y hat uni. We're calculating now basically the squared deviations, the squared residual deviations, so which is now our actual y hat multi minus our actual back depression inventory score. It's the other way around there. So we're doing C2 minus H2 squared. Can I propagate this all the way down? We're getting now a deviation from our multivariate model. So now again, quantifying this as an average. Oh, no, that we don't need. So now what we want to do is we're calculating the sum of these residual errors. Something doesn't fit right here. Oh, look at that. E3, E2. Got an error in there. Those explains the negative values. Okay. So now basically we have here a residual error of 79. What does that mean? So we have now minimized our error dramatically. So our prediction has gotten substantially more accurate. So our R square uni is basically now total minus residuals leftovers, so the leftover residuals divided by total. So that's our 0.33, right? So now the R square multi is now 788 minus the leftover error from our multivariable model divided by the total. And this has increased our R squared to 0.89, 0.9 almost. That means there's a substantial information gain and substantial increase in our predictive accuracy. That means that our model actually is now substantially more accurate in predicting our dependent variable, which essentially at the end of the day makes it much more attractive for use, right? The problem with that is that by definition, whenever you include additional variables into a multiple regression, you will always have an increase in your R squared by definition. And therefore, you use something that is called an adjustment, which is an adjusted R squared, which now Norman Hansen doesn't even show. Adjusted R squared. So an adjusted R squared is essentially nothing else. I think to show the formula. Just like so. Yeah. So an adjusted R squared is basically a formula that penalizes your R squared by the number of subjects, because your predictive accuracy is always going to get better with an increase in your sample size, and the number of variables k. So you're penalizing your R square estimate by the sample size and by the group of variables or the number of variables included, with the idea that you want to avoid that R square is increasing, and it's getting increasing to an extent that you want to include more and more variable to get that R square higher and higher and higher. Because with every increase of variable, that R square will increase. And so the adjustment, if you overfit your model and you include too many variables, that R square is actually going almost rather down than up, particularly when you have non-explanatory variables. So this is very important to keep in mind. This is a very important addition that Noren and Heinz are not touching on. Okay. So again, just for recapping. So you have unstandardized coefficients. So this is an output of SPSS. SPSS is a quite common software, particularly in psychology. In the social sciences, it's very popular. It's being now kind of not as popular anymore, and it's becoming less used by, and it's taken over in life sciences. It's basically taken over by the software called SAS, software called Python and R, which R we know, and various other softwares. But SPSS still is quite commonly used and quite commonly seen. The beauty of SPSS is essentially that you have basically, I used to have access to this. Oh yeah, still access to it. So SPSS basically, it's very popular because it allows for a visual kind of analysis of data. So it's basically a bit like Excel. It's very easy to use. Let's see what else I got then. Oh, there we go. So it's basically allowing this to be accessed in a much more visual format rather than in R, where you have to program lines and lines and lines, and you're bound to a statistical code. In the SPSS, you can utilize this in a different format where you can use this with drag and drop. So you use this quite simply, and yeah, with a visual mask, which makes it a little bit easier to use. Particularly when you start off in your journey into learning a bit more about statistics and how to use them, it's a little bit easier to use than R. R is a little bit more of a learning curve, as you already experienced. And it's going to take a bit. It's going to take a bit longer. Oh no. Okay. Can't show you some SPSS. It installed it. Is that possible? Okay, no SPSS. Okay. Successless and yeah. Okay, so you basically have here unstandardized coefficients, the slopes that you can use to estimate for each increase of your independent variables. And the constant, which is the intercept, and you can basically utilize this model to use it exactly in the same format as we have used it with the univariate model. You can, for each individual in your data set, you can then predict your actual dependent variable estimate, and you can calculate based on that your residual error and utilize this for quantifying your R squared. So the question was today is like multiple regression. When do you use multiple regression? And these are a couple of examples that essentially Owen and Heinzen have added here to that slide deck. So apps and websites, forecasting, anticipatory shipping, and shopping. So apps and websites is quite easy, right? So that's quite intuitive what is being meant there. In the end of the day, what it basically does, it takes your history of browsing and shopping, and it will calculate based on models they have for each of these products. They will anticipate when you will go shopping for this again. So they use the average time in between you use that product, and then basically suggested in exactly that time frame moving forward, they're predicting again, okay, so you may be interested in this product again because you bought it 28 days, you bought it there. So that's one possible use case. So there are several others. So forecasting, apps and websites, anticipatory shipping, that's an interesting one because not only does large online retailers not only do they predict what you may be interested in and what you may be buying moving forward, they stock their warehouses according to what they anticipate that a certain population will be buying moving forward. So they know, okay, so now it's winter, it's more likely that people are gonna buy tissues because they were congested or they have a cold. So they stock their warehouses based on previously experienced volumes that were purchased. So that makes it possible that the online retailers basically can ship to you in such a short period of time, which is breathtakingly fast nowadays, right? Shopping, same concept applies. So basically, not only will they know products that they essentially have track records of you buying, they will actually suggest products that are a consequence of what you have bought. And so there's a famous case of a father learning that his daughter was pregnant by basically she buying a pregnancy test using the father's CVS card or whatsoever. And the father basically got recommendations for vitamins that are typically for pregnant women. That was a famous case, actually made the news. So this is really how things like that are being utilized at this point in time. So you know the derivatives of shopping behavior, and you can quote unquote, it's almost manipulative. You can manipulate your customers to basically buy those products. Okay, any questions? So the take-home message really are, so regression is prediction, correlation is an association, the quantification of the strength and the direction. Regression is carrying this a step forward, basically utilizing this for prediction. You can predict variables and dependent variables using one variable only. That's a univariate analysis. You can predict it with more than one. That makes it a multivariable analysis. You mean to kind of confirm the accuracy of your prediction, and you're doing this retrospectively using a coefficient of determination, or a proportionate reduction of error. This proportionate reduction of error is basically the accuracy gained by using a regression equation over just utilizing the mean of the dependent variable. The more variables you include, your coefficient of determination will always get larger. Therefore, you use an adjusted coefficient of determination, an adjusted R-squared to basically account for the increase in variables, and thereby you essentially penalize the model for including more and more variables. That is basically to be kept in mind, because the R-square will then essentially, the R-square and other variables of comparable nature will then drive the decision of you to include variables rather than not including them. Because one thing that you would never want to do is overfit your model with variables that don't contribute to the prediction accuracy of your model. And you're comparing models against each other, and you're comparing model estimates against each other, and you're comparing the accuracy of these estimates. So yeah, a regression is ubiquitously found in your life. It's everywhere. It's on your phone, it's in your computers, it's in your online accounts, it's on the weather forecast, the prediction you have on your phone, the prediction you hear in the news. These are all meteorological models that basically also use nothing else but models of that kind. So it's really everywhere. All right, that's pretty much all that I have for today. We're gonna do a chi-squared next week. And yeah, have a nice holiday, long weekend, and see you next week on Monday. Bye-bye.